Welcome back to the wonderful world of physics. This is the beginning of chapter 28 for Physics 104B on alternating current circuits. And we start with section 1, alternating current. Thinking back to when we studied thermodynamics, we looked at how a steam turbine works, and the idea that I presented was that you have a region of high temperature and high pressure steam, that's here on the left, and low temperature, low pressure steam, that's there on the right. And because of the differences in temperature and pressure, the wheel, the turbine, is able to turn. And when we learned this in class, I said, this is how electricity is generated. This is a generator, so let's get more into that. Now we've learned that if you have a magnet and it's rotating, so we'll attach a magnet to this turbine and it's rotating, then we have a constantly changing magnetic flux in this region. And now let's put a conducting loop right here, and the magnetic flux is going to continuously be changing. And as it's continuously changing, going up and down and reversing direction, you're going to get a current that is getting generated continuously, and it keeps going back and forth, and that is how alternating current is produced. So with alternating current, it's sinusoidal, both the voltage and the current. And the voltage and current can be characterized by the amplitude. So we call that the peak voltage and the peak current. And you can look at these graphs below, just a simple sine curve that has not been phase shifted. And so remember, sine curve is going to start at 0, go up to some peak, and go down, and then come up again at 2 pi. And it can be characterized by its frequency and also the phase constant. Now, amplitude can also be expressed not as the peak, but as the root mean square. Root mean square for voltage and current are more useful for practical situations and for engineers because they convey more, they can be used to compute how much power can be delivered. And I don't go through the derivation here. I just get to the result that the root mean square of voltage is the peak voltage divided by the square root of 2. And the same for current. The root mean square of the current is the peak current over square root of 2. So in the United States and Canada, standard line voltage is 120 volts, and that's actually the root mean square. You can do the calculation from those equations up at the top, and you can see that the peak voltage is actually 170 volts. But because it's swinging between 170 volts and 0, the more useful term is the 120 volts, the root mean square. I want you to remember from first semester that angular frequency, we measure that in radians per second. Sometimes we just write that as per second, and that's omega. Whereas frequency, F, is measured in hertz, or cycles per second. And the relationship between them is omega equals 2 pi times F. When thinking about the sine curve and the equation that goes with it, there's a phase constant. The phase constant tells when the sine curve crosses 0 with positive slope. And the thing you need to remember when you're dealing with a phase constant in an equation such as the 2 on the screen is that if it's a positive sign, if it's a plus sign, then you can think of it's the sine curve. So it would be sine omega t, but shifted to the left by phi. And if it's a minus sign, then it's shifted to the right. And so here you can see the full equation, the sinusoidal equation, both for voltage and current. And the subscript P means peak voltage and peak current. And so here we have the voltage, the sinusoidal curve, and it's phase shifted just a little bit. And so notice it's not starting at 0 at the origin, but rather the voltage is at 0 some little bit, whatever that phase shift is to the left of phi. And it says here down below, the sine curve starts at omega equals negative pi over 6 or 30 degrees before t equals 0. So the phase shift in this case is to the left, pi over 6. Let's look at an example in the book. Example 20.1 for characterizing household voltage. Standard household wiring in the US supplies 120 volts, that's root mean square volts, at 60 hertz. Express this mathematically as a sine function, assuming the voltage is rising through 0 at time equals 0. So we're going to start with our basic equation down below. You see that? It says assuming the voltage is rising through 0 at time equals 0. That means that it's not phase shifted. It's just a standard non-shifted sine curve. Let's look at the given information. The V RMS is 120 volts. Frequency is 60 hertz. We're going to want to know the peak voltage, and that's square root of 2 times the root mean square voltage. That's 170 volts. We're going to need omega for the formula. So omega is 2 pi times the frequency. So 2 pi times 60 hertz is 377 radians per second. And because it's starting at 0 when time is 0, we're going to say the phase shift is 0. So applying all these quantities into the equation, we get that the voltage is 170 times sine of 377t volts. And that is the end of chapter 28, section 1. Have a great day.